Our next speaker is going to be talking about errors related to weak memory in GPUs. I just want to say a couple things about GPUs. GPUs are actually being used heavily in cars now. It's an interesting problem. All the self-driving features of cars actually require tons of computation, a lot of vision processing, etc. So this is particularly important to the question about when you drive your car around, are there problems? So in particular, I just want to welcome Tyler Sorensen from Imperial College, who's going to be telling us about GPU errors in with weak memory. Thanks.
All right, can everyone hear me? What's up? All right, thanks for the introduction, Ben. Like you said, my name is Tyler Sorensen. I'm a PhD student at Imperial College London, and today I'm going to be talking about exposing errors in GPU applications, and specifically errors related to weak memory effects. This is joint work with my supervisor, Alistair Donaldson. So let's jump right in with an example. The NVIDIA book, CUDA by Example, gives a GPU dot product implementation. And it looks like this. So it's simple enough we can kind of show it on a slide. But if we look at it, there's some, let's see, memory accesses up there, there's some mutex, and in the implementation of the mutexes, there's some read, modify, write instructions. So even though it's a simple application, there's still some interesting things going on here with respect to concurrency. Given a program like this, how might we go about testing it? Well, I think the easiest way to test a program is to just actually run it and see if it does the right thing. So that's what we did with this one. We downloaded the code and we ran it repeatedly for 1 hour. It took about 2 seconds per iteration. And after each iteration, we checked for errors. And the reason why you want to run a program like this multiple times is because it's a parallel algorithm with non-deterministic interleavings, and you want to try to test as many interleavings as possible. So we did this. We didn't observe any errors. So the code is probably correct, right? It's pretty simple. Well, we would be wrong. Previous work that I was involved with from 2015 in AlBassam showed that this application actually contains a bug due to weak memory model effects. So in our previous work, if we said there was a bug, but we don't actually observe the bug when we're running the application, how did we know there was a bug? Well, we stared at the code really, really hard. We thought really, really hard about the different executions of the code, and we thought really, really hard about memory models. And from those, we concluded that there was a bug. So I hope everybody in this room can agree that that's not a good testing method. It requires experts, it's tedious, and there's no guarantees, and it's prone to human error. So in this work, what we set out to do is to design a method so that programmers who maybe aren't experts in memory models or program analysis can actually use to test their applications for these types of bugs. And after that, the icing on the cake is we'd like to automatically suggest ways to fix bugs if we do encounter them. So how did we do this? Well, we developed a stress and fuzz testing environment specifically designed to reveal weak behaviors in GPU applications. And now when we take the same application, and again we're going to run it for 1 hour, again 2 seconds per run, check for errors, we actually observe 396 erroneous runs. So great, we were able to expose the error and actually see the error affecting the result on real GPU hardware. So that's only the first part. The second part we'd like to know is how can we fix this bug? Well, let's go back to the code. Previous work on memory models have shown that if you insert a special instruction called a fence before every single memory operation, you should get, it should disallow all weak behaviors. So let's do this. We've added these thread fence instructions. There's 5 of them. And let's run this code again in our testing environment. Again, for 1 hour, about 2 seconds. We didn't observe any erroneous runs when we do that. So can we say that we fixed the application? I would say no, because these fences can have a high performance overhead. And with those 5 fences that we added to that application, if you profile it, that gives a 60% runtime and energy overhead. GPUs are called accelerators, not deaccelerators. So this is probably not acceptable. Let's go back and look at the application. Well, previous experience kind of tells us that all of these fences are probably not necessary to disallow the bug. And in fact, in our previous work, we showed that you only need 1 fence. But can we do this automatically? So we use our testing environment in a greedy algorithm that examines each fence, it tries to remove it, then it tries to run the application. If it observes an error, it puts the fence back in, otherwise it keeps the fence removed. And if you do this, it converges to a single fence. And now recall that we had a 60% runtime and energy overhead. With that single fence, we get that down to less than 3% runtime and energy overhead, while still not observing any errors, even in our testing environment. And I should put a disclaimer here. When I talk about fixing these bugs, I'm talking about empirically fixing these bugs, not necessarily formally fixing them. We're just trying to disallow observable errors in our testing environment. Cool. All right, so now that we've gone over an example, here's the outline of the talk. We'll go into some more details. First, I'll give a background on what we actually mean by memory models and weak memory behaviors. Then I'll talk about how we developed our testing environment, specifically to reveal weak memory bugs. Talk about how we evaluated the environment. And then finally, I'll talk about the fence placement routine. So let's get started with some background. What do we mean by weak memory models? Well, one way people like to think about weak memory models are through what are called litmus tests. That is, these short concurrent tests with an assertion about the final state of registers. So here we have an example of a litmus test. We have an initial state where we have two memory locations, x and y. They're both initialized to 0. Then we have a short concurrent program and this assertion. And this particular test is called message passing. And it tests how two threads can implement a handshake idiom. So in particular, we say we store some data in the x memory location and a flag in the y memory location. What this test is asking is if thread 0 can store some data, then store a flag, and then if thread 1 can read the flag, followed by the data, and what we want to know is if thread 1 can observe the updated flag, yet still observe stale data from the initial state. So how can we check this little program to see if that assertion will pass? Well, one way that people like to reason about concurrent programs is by looking at interleavings. So let's do that real quick. We have this program, and let's start interleaving the instructions and see what happens. Well, there's one interleaving where thread 0 executes completely before thread 1. There's another interleaving where you mix them up a bit. You can keep doing this until you see 6 possible interleavings. And in none of those interleavings is that assertion satisfied. Okay, so now that we've done our program analysis on this little test, can we assume this assertion will never pass? Well, the answer actually is no, and this is because of weak memory models. Architectures implement what are known as weak memory models. This is where hardware is allowed to reorder certain memory instructions. And when they do this, executions can be allowed that don't correspond to an interleaving of instructions. And these executions that don't correspond to an interleaving are what we call weak memory behaviors. Cool. Okay, so now let's actually get on and talk about the testing environment, how we designed a testing environment to try to expose these types of behaviors. So our overall goal is we want to reveal weak memory behaviors in GPU applications in a black box style. We don't want to know anything or much about the application. We just want this testing environment that's able to do this. So the way we accomplish this is with 2 heuristics. I'm only going to have time to talk about one of them, but you can read about the other one in the paper. So this heuristic we call memory stress. And what happens in the GPU application is you allocate, say, n threads, and these n threads actually run the application code. And then these threads have a region of memory that they store the data of the application in. So this is pretty straightforward. What we do in memory stress is pretty simple. We add extra threads, a bunch of extra threads, because GPUs can handle a lot of threads. And these threads do not run the application. They run a routine, which we call memory stress, and they do not touch the application memory. They have their own region of memory, which we call scratchpad memory. And so while this picture looks pretty simple, once you start implementing this, you realize there's a lot of choices to make. This memory stress routine, you have a lot of threads that can be doing a lot of different things, and your scratchpad location can be quite large, so you have a lot of different memory locations that you could access. And what we want to do is best utilize these extra threads such that their behavior over here, memory stressing, actually causes weak behaviors to occur over there in the application land. So the way we design this memory stress is through micro benchmarks. And luckily we have past work on memory models gives us some good litmus tests, like I showed earlier. So we're going to take these litmus tests as micro benchmarks and try to tune this memory stress based on these. So here I'm showing 3 litmus tests. We have message passing, which I talked about earlier. Then we have load buffering and store buffering. I'm not going to go into too many details about load buffering and store buffering, other than load buffering checks to see if loads can be reordered with program order later stores. Store buffering checks to see if stores can be reordered with program order later loads. And the 2 things, though, to notice about these is all of these litmus tests just have 2 memory locations, X and Y, and all of them also only have 2 threads. Okay? So now that we have some micro benchmarks, oh, and I should say, the reason why we picked these 3 litmus tests is because when we looked at previous memory model bugs found in previous work, if you drill down and look at those bugs all close enough, they all correspond to one of these 3 idioms. We aren't really, I know there's more weak behaviors and more litmus tests, but we're not aware of any documented bugs that actually correspond to these other weak behaviors that can occur. Okay, so now that we have our micro benchmarks, the first question we might want to ask is, we have that large scratch pad. Where can we test in that scratch pad? So now we're going to instantiate our micro benchmarks. Remember that we only had 2 memory locations in those litmus tests, X and Y. And so we're going to try a variety of instantiations of those litmus tests. So we're going to try one where X and Y are right next to each other in memory. Then we're going to try spacing them out a little bit, spacing them out a little bit. We're going to keep doing this up to a threshold D. And this is because we want to try to mimic weak behaviors that could happen in applications. We don't know where X and Y are in applications, so we're going to try to get a decent coverage here. And then for each scratch pad location, I, we're going to just hammer that single location with reads and writes. And then we're going to go and try to hammer the next location, and so forth. So this is really a nested for loop for each distance, for each scratch pad location I, and then we're going to run each micro benchmark 1,000 times, just stressing that single location. Okay? And I have a nice visualization of the results. I'm going to show you the template real quick so you can understand them. Right here we have our distance D. Remember, that's a distance between X and Y, and this is in memory words. Then we have our index I stressed. Remember, this is in the scratch pad. This is the single location that we're hammering with reads and writes. We have our 3 litmus tests. And what we're going to do is, if we observe a weak behavior, we're going to draw a vertical bar right there. And the size of the vertical bar is going to correspond to the number of weak behaviors we observe. Recall that we're running these for 1,000 iterations. So, for example, if we only observe 1 or 2 weak behaviors out of the 1,000, that's going to be very short. Where if we observe 500, that's going to be quite long. So I'm actually going to pull these results up. Let's see. Oh, perfect. Okay, so here are some test results for a GTX Titan, which is a high-end gaming GPU. Okay, so I'm going to pull this up, and this is going to look exactly like that template because we don't see any weak behaviors. We're at distance 0, and no weak behaviors are here. So let's scroll through some of the distances. We're starting to increment that. We're not seeing weak behaviors. So we could start to get pretty depressed. But hopefully there's something, otherwise I probably would be up here. 32 is a magic number in computer science. And actually that says 31 because I have it off by 1 error. But we start to get things like this. And as I scroll through these distances, these patterns look fairly similar until we get up to the next group of 32 distances. We change the pattern, and we can keep going. I mean, it is kind of fun to scroll through these. These are kind of fun. And I think there's actually a lot of information you can get out of these graphs. But what I'm interested in is what data I can get from my testing method. And what data I see here is that these weak behaviors, when they occur in groups of 32. So for example, on this one, if I was trying to get MP to appear, I could stress index 32, index 33, index 34, and I'd get roughly the same result, up to 64. So this is actually really interesting and good for testing because that means we've just cut our search space for our stress down by a factor of 32. So a question might be, does this hold for other architectures. So let's look at that one was a Kepler GPU. Let's look at a Fermi one, which is the older model. Okay, so again, start off, no weak behaviors. Scroll up, all of a sudden we're past 32, no weak behaviors, so we might start to get worried. But then up here at 64, we see the same sort of thing, but rather than being in groups of 32, they're in groups of 64 here. So, I mean, we could keep looking, and it would do roughly the same thing as the previous one. Okay, good. So we have Fermi and Kepler GPUs. We can just look at one more real quick. This is the Maxwell GPU Architecture, a newer one. And this one gets a little interesting. So you can see there's, even at distance 0, we get some noise on message passing. We can scroll up to 64, and our pattern doesn't appear here. We actually just see kind of noise everywhere. But if we keep testing, we don't get too discouraged, we'll see around 128, we start to see that pattern again. And finally, at the very end, we see, let's see, that pattern appear for message passing as well. So, we have those results, and what that tells us is when we're thinking about where to stress in the scratch pad, we don't have to stress every single location, we only need to stress every 1 in 32 or 64, depending on the architecture. Yep, and we're going to call a region of these elements a patch. So for the GTX Titan, a region of 32 elements would be a patch. For Fermi, a region of 64 elements would be a patch. Okay, so the next thing we might want to know is how many of these different patches can we effectively stress? So if we look back at some of these samples, if we wanted to reveal MP behavior, you can see over here we'd want to stretch the patch between 32 and 64 for distance 129, but if we had distance 227, we'd want to stress a different patch for message passing. We'd want to stress the patch from 64 to 96. Hopefully you can see that going back and forth. So we'd like to stress as many of these as possible. So the next micro benchmark we set up was how many patches we can stress. We're going to set it up to have a scratch pad to have a size of 64 patches, and we're going to randomly select one patch in those 64, and then we're going to try randomly selecting 2 patches, randomly selecting 3, 4, up to 64. And what we get is a graph that looks like this. On the x-axis, you have the number of different patches we're trying to stress, and on the y-axis, you have the number of weak behaviors that appeared. So this is actually pretty interesting, because I thought the more patches you tried to test, the more weak behaviors you'd get, because you're covering more of these patches. But it turns out you actually need to be pretty concentrated. And if we zoom in up here, we actually see for all 3 of the tests, message passing, load buffering, and store buffering, it's optimal to only try to stress 2 random patches. All right, so now we have a memory stressing strategy. We actually worked on tuning the different memory instructions that you can use in your memory stress, but I'm not quite sure I'll have time to go over those. So let's talk a little bit about our evaluation of our environment. We tested about 10 different applications. We didn't really have a huge application pool to use because most GPU applications don't use fine-grained concurrency. Most of them use the bulk-grained concurrency through the GPU primitives. So we were able to find 10 to test. And we tested these applications on 7 NVIDIA chips, and we covered 3 architectures, the ones that I showed the graphics for, Fermi, Kepler, and Maxwell. And our experimental setup is we run these applications for 1 hour, and we've written a post condition in each of these applications to check for errors. All right, so here is a list of the chips that we tested, and we're going to run them without stress and then with our stress. So, and this is the number of applications that we observed errors in. So you can see for most of these chips, you can run these applications for an hour and not observe any errors. We only observe errors on 1 application for 2 chips. Now if we add our stress, that jumps up to this. We're able to observe errors in 8 applications almost across the board, except on the GTX 980, where we only observed errors in 7 applications. So just some high-level results of these applications. I don't have time to get into each of these applications and what they actually do, but we provided empirical confirmation of 3 bugs found in previous work. That's the previous ASPLOS work I mentioned at the beginning. What happened in that work is through hand analysis, we found a bunch of bugs, but we never actually observed them. Here, we provide confirmation of 3 of them. We actually observed them running on hardware. And we discovered 2 new weak memory model bugs in applications. Right, so let's talk just a little bit about fence placement. This is actually pretty simple, so I won't spend much time on it. You start with the conservative fence placement, that is, you place a fence before every single memory operation, and then you go through these fences and you try to remove them. At every removal, you run the application again under the testing environment. If you observe an error, you put that fence back in. If you don't, you leave that fence removed. And so here are some results for that. Here's our applications. Here's the number of fences that you have in the conservative case. And when we reduce them, it gets it down to those numbers. So in most cases, applications only needed 1 fence. For our big application, which is from the GPU Lone Star suite, Barnes Hut and body simulation, we actually needed 4. That's our big application. But you might not care too much about the number of fences. You might actually care about how the fences impact performance. So let's look at some high-level results on those. The median overhead of reduced fences is 4% energy and less than 3% runtime. But if you have your conservative fences, you pay a lot more. You have a median of 63% energy and 59% runtime. So this shows that fences on GPUs can be extremely expensive, but you can reduce them with fairly high confidence using a method like this. Okay, so that actually brings me to the conclusion. You can use stress and fuzz testing to effectively reveal weak memory bugs in applications. You can tune the stress based on micro benchmarks, and it's best tuned per architecture. And then finally, fences can be costly, but you can reduce them using testing and fuzz testing and checking that. So that's it.
So we've got time for some questions. Let me just shoot out the first one. So what's magic about 1 hour?
Oh, that seemed like it seemed like a reasonable amount of time that an actual developer would spend testing the application. And also, it was actually tractable because we tested 7 GPUs across 10 applications, so that's already 70 hours of testing across all those.
So is it possible that by reducing the number of fences, you got to a point where you didn't observe an error in the 1 hour period, but if it looked longer, they might still be there? It's just not showing themselves as often?
Yeah, and in fact, we have one case of that where we see an error, but it just shows up so rarely, and the fences, our method ends up saying, you don't need that fence, but if you run it for a bit longer, well, not a bit longer, actually quite a bit longer, then that error can crop up. So like I said at the beginning, it's an empirical fix. You can think of it more like hardening the application rather than fixing the application.
Hi, thanks for the talk, it's really good. There's been some work on doing this sort of static analysis for this for CPUs using like critical cycles as the formalism.
Mm-hmm.
Do you have any sense for how this relates, or like maybe that doesn't scale particularly well for the applications that you looked at, or why it wouldn't work in this case?
Yeah, so first off, the tools that I was able to find that did that worked on C++ code, and I tried adapting the CUDA to it, and it actually ended up being quite difficult, and I tried to work with some of the authors, and we couldn't get it working too well. The other thing about this approach is those critical cycles require a formal memory model. CUDA doesn't have a formal memory model. You kind of hit a dead end there. The other issue with that, let's see, is with these applications, those critical cycles will, as far as I'm aware, work to restore sequential consistency. a lot of these applications probably don't need sequential consistency. They just need a couple of these weak behaviors disallowed. So it's definitely a related approach, but there's some differences as well.
Thank you.
Yeah.
Can you see from those required fences anything about what the developers were failing to understand in this code?
Yeah, actually, quite a bit. So in about 3 of them, they were in mutex implementations. They just needed a fence with the unlock method. So you can kind of see that these could be abstracted. If you were given a mutex library, these bugs wouldn't, correctly implemented mutex library, these bugs wouldn't be that. The other ones were like concurrent data structures, sort of in the places you might expect, pushing and popping right after atomically modify right, stuff like that.
But could one see, for example, that they were thinking of this like an x86?
Ooh, that's a good question. I didn't notice that in when I looked at the code, but perhaps. Maybe I'll go back and look at it.
Thanks for your talk. This is a really simple question on the slide right before this. You just showed the neediness. Is there some reason that you don't just show that? Are those characteristic of the whole distribution, or?
There were some nasty outliers, so that's why if we showed the average, it would be pretty awful.
You're so honest. Okay, great. Thank you very much.
Yeah.
Okay, let's thank the speaker.